始めます。それで、PDF、ここです。ここで、ダウンロードできます。それから、だいたい48ページぐらい。この辺からやります。それで、OK だよね。OK だと思います。で、ここまでやったと。で、if we apply this expansion to the integrals 271 and 272 and replace mu by epsilon f in the terms already of order t square in these equations, we find these. So this is a kind of the conclusion up to now. The temperature independent first term on the right side of 274 and 275 are just the value of u and n in the ground state. Since we are calculating the specific heat at constant density, n is independent of temperature, and 275 reduces this. This has to be 0. So this has to be 0. Okay. Which determines the deviation of chemical potential, deviation of the chemical potential from EF. So mu is equal EF minus pi square divided by 6 kBt square times G prime divided by G. Okay. Since for free electron G of epsilon varies as epsilon to the power 1/2, equation 263, this gives mu equal EF, epsilon F, multiplied by 1 minus 1/3 pi kBt divided by 2 epsilon F to the power square, which is, as we asserted above, a shift of the order of t square, and typically only about 0.01% even at room temperature. Anyway, epsilon 1/2. Shall we calculate here? Okay, epsilon 1/2 is if G goes to epsilon 1/2, G prime goes like 1/2 epsilon minus 1/2. So G prime divided by G goes like 1/2 epsilon minus 1/2 divided by epsilon minus 1/2, which divided by epsilon 1/2, which is 1/2 epsilon inverse. Okay, so this one this thing is 1/2 epsilon inverse. Then we put EF here. So that means this second term goes like minus pi square divided by 12th of kBt square epsilon f 1/epsilon f. Then we put epsilon f outside, so this we put epsilon f outside, so this becomes like epsilon f square. Then what is that? Then we put 2 inside. So we 3, we put 4 here. And we also put pi inside. Pi kBt divided by 2 epsilon. Pi kBt divided by 2 epsilon square. Yes. Which is, I already read this. Equation 276 sets the term embraces in 274 equal to 0. 676. Okay. Thereby simplifying the form of the thermal energy density at constant electronic density. So this is 0, and actually this is also 0. So this means this part is also 0. Is it correct? So then energy thereby simplifying the form of thermal energy density at constant electronic density. So this is the form of thermal energy density at constant electronic density. U equal U0 plus pi square over 6 kBt square times G of epsilon f, where U0 is the energy density in the ground state. The specific heat of the electron gas is therefore CV is partial U partial N partial T at constant N equal pi square over 3 kb square T G of EF, or free electrons. So we replace G of EF using N. I think I don't have to check this. We accept CV equal pi square over 2 kBT divided by epsilon F n kBT. Comparing this, okay, actually here I think we should notice this result is proportional. Let me write proportional to T. So free electron specific heat is proportional to temperature. This is the main result we should remember. Comparing this with the classical result for an ideal gas, CV equal 3 nkb over 2, we see that the effect of Fermi-Dirac statistics is to depress the specific heat by a factor of pi square over 3. Pi square over 3 times kBT epsilon E over epsilon F, which is proportional to the temperature, and even at room temperature is only order 10 to minus 2. This explains the absence of any observable contribution. Okay, so this is, let's see, this value is 0.01. Then pi square over 3 is about 3. So this is like 0.03. So this is actually underestimating or overestimating result. Okay, because the factor should be just 0.03, right? But it is overestimating to 0.01, overestimating the effect. This explains the absence of any observable contributions of the electronic degree of freedom to the specific heat of a metal at room temperature. Absence of any observable contribution. Okay, so we actually find by experiment or something, we find the absence of observable contribution of the electronic degree of freedom to the specific heat in a metal at room temperature. And that's because of this. If one is willing to dispense with the if one is willing to dispense with the precise numerical coefficient, one can understand this behavior of the specific heat quite simply from the temperature dependence of the Fermi function itself. The increase in energy of the electrons when the temperature is raised from 0 comes about entirely because some electrons with energy within order kBt below EF, the darkly shaded region of figure 2.4, have been excited to an energy range of order kBt above epsilon f. The lightly shaded region in figure 2.4, the number of electrons per unit volume that have been so excited is width kBt of the energy interval times the density of levels per unit volume g of epsilon f. Furthermore, the excited energy is of order kBt, and hence the total thermal energy density is of order g epsilon f kBt square above the ground state energy. This misses the precise result 279 by a factor of pi square over 6, but it gives a simple physical picture and is useful for rough estimates. Figure 2.4, the Fermi function at non-zero temperature. The distribution differs from its t equals 0 form because some electrons just below EF darkly shaded region have been excited. I think darkly shaded region is this. This is darkly. Have been excited to level just above EF. This is a lightly excited region. This one. Lightly shaded region. Lightly shaded region. The prediction of linear specific heat is one of the, the prediction of specific heat linear to temperature. Prediction of the value of specific heat linear to temperature is one of the most important consequences of Fermi-Dirac statistics and provides a further simple test of the electron gas theory of a metal, provided one can be sure that degree of freedom other than the electronic ones do not make comparable or even bigger contributions. provided one can be sure that degree of freedom other than the electronic ones do not make comparable or even bigger contribution. As it happens, the ionic degree of freedom completely dominate the specific heat at high temperatures. However, well below room temperature, their contribution falls off as the cube of the temperature, see chapter 23. And at very low temperatures, it drops below the electronic contribution, which only decreases linearly with T. In order to separate out these two contributions, it has become the practice to plot Cv over T against T square for if the electronic and ionic contributions together result in the low temperature form, constant volume specific heat equal gamma T plus AT cube. Then Cv over T equal gamma plus AT square. One can thus find gamma by extrapolating the curve, extrapolating the Cv over T curve linearly down to T square equals 0, and noting where it intercepts. Noting where it intercepts the Cv over T axis, measured metallic specific heats typically contain a linear term that becomes comparable to the cubic one at a few degrees Kelvin. Linear term that becomes 25. Since constant density is hard to arrange experimentally, one generally measures the specific heat at constant pressure Cp. However, one can show problem 2 that for the metallic free electron gas at room temperature and below, Cp over Cv equal 1 plus order kBT divided by EF square. Thus, the temperatures where the electronic contribution to the specific heat becomes observable, a few degrees Kelvin, the two specific heats differ by a negligible amount. Anyway, we did this. Specific heat data are usually quoted in joules or calories per mole per degree. In joules or calories per mole per degree Kelvin. Sorry, let me answer. I can copy paste. Specific heat data are usually quoted in joules or calories per mole per degree Kelvin. Since a mole of free electron metal contains G times Avogadro number conduction electrons, where G is the valence and Na is Avogadro number, and occupies a volume GNA divided by small n, we must multiply the heat capacity per unit volume CV heat capacity per unit volume CV by GNA divided by N. Anyway, in order to get the heat capacity per mole, C. So C equals pi square over 3 GR. R is kV Na equals 8.314 joule per mole equals 1.99 calories per mole Kelvin. This is strange. Joule per mole. Do I need Kelvin here? Yeah. Joule per mole Kelvin. 1.99 calories mole Kelvin per mole Kelvin. Using the free electron density of level 2.65 and the evaluation 2.33 of epsilon F divided by kV, we find a free electron contribution to the specific heat capacity per mole of C equal gamma T. Free electron density of levels and evaluation of epsilon F divided by kV. Where is the epsilon F divided by kV? Okay. We use free electron density of levels. We use it here. Then, where do we use evaluation of 33 of E epsilon F divided by kV? So we have this value in 233. So from this we put EF value here, I think. Then we find a free electron contribution to the heat capacity per mole. Then gamma, where gamma is 1/2 pi square R. I don't think I will work out. I think this derivation is not difficult, so I can just accept the result. We find a free electron contribution to the specific heat capacity per mole of C equal gamma T, where gamma equal 1/2 pi square R G over TF equal anyway 0.169 G times Rs divided by A0 square times 10 to the minus 4 calorie mole inverse Kelvin square inverse. Some rough measured values of gamma are displayed in table 2.3 together with the free electron. Some rough measured value of gamma are displayed in table 2.3 together with the free electron values implied by 285 and the values of Rs divided by A0 in table 1.1 together with the free electron value implied by 285 and the value of Rs divided by A0 in table 1.1. So that note that the alkali metals continue to be reasonably well described by free electron theory, as do the noble metals copper, silver, gold. Note also, however, the striking disparities in iron and manganese experiment of the order of 10 times theory, as well as those in bismuth and antimony experiment of the order of 0.1 times theory. These large deviations are now qualitatively understood on fairly general grounds, and we shall return to them in chapter 15. So this is some rough experimental values for the coefficient of the linear term in T of the molar specific heats of metals and the values given by simple free electron theory. So this gives effective mass. Since the theoretical value of gamma is proportional to the density of levels at the Fermi level, which in turn is proportional to the electronic mass m, one sometimes defines a specific heat effective mass m star so that m star over m is the ratio of the measured gamma to the free electron gamma. Beware of identifying this specific heat effective mass with any of the many other effective masses used in solid-state theory. Beware of identifying this specific heat effective mass with any of the many other effective masses used in solid-state theory. For example, the index entries under effective mass. Anyway, so lithium, it's okay. This is just ratio, gamma ratio. So this is the same as gamma ratio. Gamma ratio. So lithium, sodium, potassium, rubidium, cesium, copper, gold, silver, beryllium. Beryllium is very bad. Magnesium, calcium, strontium, barium, niobium. Niobium is very heavy. Niobium, iron is also heavy. Manganese, very, very heavy. Very heavy. Zinc is okay. A little bit light. Cadmium or cadmium. It's light. I thought it's heavy. It's light. Okay. Mercury is heavy. Free electron in mercury is heavy. No, it's okay. Just double. Okay. So sorry. This cannot be compared. This should be compared. Because this is it's okay. Aluminum, gallium is light. Electron mass of gallium is light. Indium, not so heavy. Thallium, tin, lead. Bismuth is very light. Very light. Magnesium is very heavy. Magnesium is very heavy. Interesting. Bismuth is light. Antimony is also. See, I can show you. This is there is bergman. Weak localization. Weak localization in thin film. I hope this allow free download to PDF. Purchase PDF. See, this is not free. Access through your what is this? Is this bergman? I can just copy paste. No PDF. There has to be PDF. Universal scaling of weak localization in graphene due to universal scaling. Sorry, I want to see this. Who is this? Oh, when was this published? When was this published? 2020. What is a universal scaling? Ooh, not so clean. Oh, nice. Okay, anyway, let me see. Where is the PDF? I don't know if I can find. Behavior graph. Anti-localization in topological spin polarized. Let me see. 消しちゃった。PDF。Okay, I think I give up. We can go to this. Then there should be abstract. A resistance two-dimensional system such as thin-ordered film shows deviation from Boltzmann theory, which are caused by quantum correction and called weak localization. Theoretically, weak localization is originated by the Langer-Neal graph in the Kubo formalism. In this review, article of physics of weak localization is discussed. Oh, this doesn't say. Okay, then let's go physical review B. So this is physical review B. This is physical review B. This is physical review B. No. Okay, I just wanted to show you that some experiment of weak localization was done using magnesium film. And magnesium, very interesting. So, magnesium, okay, sorry, that was not manganese. Magnesium. So, manganese is different material. Manganese is very heavy in electron mass, okay, and gold is about 1.6. So because this weak localization experiment, manganese film, the sample was prepared, deposited manganese film, then measured electrical resistance of this manganese film at low temperature as a function of gold particle density. They deposit very small amount of gold on top of manganese film. So the electron in the manganese film interacted with gold, which is a kind of spin orbit interaction. So then found very nice scaling result. This was published in 80s by Bergman. So anyway, I think we reviewed these property of metals. So I can now stop today, then continue next time. Next time we do from here. Sommerfeld theory of conduction in metal. What is the page? Page number 49.